Thank you, Crystal. I I almost forgot. Yeah, thank you. All right. So yeah. So A. So here. Uh, yeah, no problem. No worries, Ibrahima. I got you. So A here would be equal to half, right? So your constant A, it could be a whole number, it could be a fraction, it could be a decimal, for example. So V. So this f of x, of course, is an exponential function. Okay, is exponential. Another example, example 3. F of x equals to, so as I said, it could be also, A could be a decimal. So for example, 3.1, 2, 3, 4, etc. Let's say to the power x, all right? So A, your constant A is the 3.1234, right? So this is another example of exponential functions, right? This is an exponential function, is exponential. Now, if you have, if your A is equal to 1, so the problem with 1 is that, so for f of x equal to 1 power x, so you would say A is equal to 1, but the problem here is that, I mean, because the thing is 1 to the power x is equal to 1, all right? So, I mean, 1 to any power would be equal to 1. So this is a constant function. It's not really an exponential function. So this is constant. So it's not an exponential. All right. So you need your A to be different from 1, because otherwise, you would end up with a constant function. Good morning, Kismat. Yeah, thank you. I got you. Thank you. Not an exponential. As I said, your A must be positive. So for example, if you have f of x equal to negative 3 to the power x, this is not, is not an exponential, because again, you need A to be positive. Okay, because A is negative. Because A, which is negative 3, is negative. It's negative, right? And last example, 6, if you have, let's say, f of x equal to x to the power x, right? So this is a possible function here. I mean, you have x to the power x. So as I said, your A. So A, by the way, A is called the base. Okay, so the A is called the base. So your A here, it would be x, but x is not constant. X is a variable. So this is a variable, not a constant, right? So this is not a constant, right? So your A in this case would be x, but x is not constant. X is your variable, is your input, right? X varies, right? It's not a constant, so is not constant. So then this function x to the power x is not, so this is not exponential function. So this is not an exponential, right? So anyway, so what you have to keep in mind, guys, when I say exponential function, I mean some constant, this A here, some constant to the power x, right? And again, so this A here is called the base. A is called the base, right? So we have some constant. So the constant must be positive and different from 1, right? Now, if you try to graph exponential functions, so what will be the properties of the graph of exponential functions? So So this is the properties of the graph of exponential functions. Okay, so keep in mind our function is, so our f of x is some a a to the power x, right? Where a is a positive, right? It's just a positive constant, right? So first thing, first question we can ask here is, what will be the domain of such a function, right? So a to the power x. So what will be the domain of this exponential function? Well, here there's no, there's no division, there's no, so there's no division. So your a, or your input x, could be actually, it could be any real number. So first remark is that x, and of course a is positive number, right? So then x, it could be any real number. So there's no restriction on x. Okay, so the domain would be just the domain would be the whole number line. So it's negative infinity, positive infinity. Right. Of course, if you can imagine, if x is, let's say x is equal to half, x is equal to half, so there will be a square root. But then the thing is, a must be positive, and the square root of positive number, that's it's well defined, right? So that's why we require, that a is positive, right? So even if you want to take like a to the power half, if x is equal to half, then it makes sense because your a is positive. So yeah, so the domain here is your input x could be any real number, right? Now, what about the range? Well, here, because a is positive, a is some positive constant to the power x. So a to the power x is going to be a positive number. So because a is positive, so a to the power x is a positive number. Okay, and actually it cannot be equal to 0 because a is positive, a is not 0. So a to the power x is a positive number. So that means that the range would be 0 excluded, okay, positive infinity. It's again, 0 is excluded because a is positive. A cannot be 0. If a is 0, then yes, 0 to the power x would be 0. So you can have 0 in the range, right? But a is not, is different from, it's positive, cannot be 0. So then a to the power x is actually always a positive number, right? What else? Yeah, what about the x-intercept? 2. So what about the x-intercept? So you want to find the x-intercept of this exponential function a to the power x. So we have to solve. Remember how we find the x-intercept? We have to solve f of x equal to 0, right? So in other words, I have to solve a to the power x equal to 0. But again, remember, guys, we said a is positive number. A cannot be 0. So a to the power x equal to 0 has no solution because a is positive. So this equation here has no solution because a must be positive, because a is not 0, because a is cannot be 0. Okay, that's by our definition, right? We said a must be a positive number, so a cannot be 0. Right? So there's no solution to this a to the power x equal to 0. So there is no x-intercept. So whenever I want to graph exponential function, then actually there's no x-intercept, which means that your graph doesn't intersect the x-axis. So the graph of the exponential functions, the graph of exponential functions, okay, do not intersect the x-axis. All right. Now, so there is no x-intercept to this function, exponential function. Okay. Now, what about the y-intercept? Well, so y-intercept of exponential functions. So y-intercept. So we have to plug 0 in the function, right? So that's how we find the y-intercept. We have to evaluate f of 0. So my f of x, again, my exponential function is a to the power x, right? So we have to evaluate f of 0. So that will be a to the 0. So a to the power 0, of course, that will be 1, right? Any non-zero number to the power 0 is 1. So then there's y, so there's a y-intercept, and that will be 0, 1. So the y-intercept is 0, 1. 0, 1. So when you graph your exponential function, you have there's an intersection with the y-axis, and that will be the intersection would be at 1, right? So what else? Let's see. Yeah, so this is like general properties of any exponential function. So in general, so for example, if you want to graph, let's say you want to graph, so examples, right? So let's say you want to graph f of x equal to 2 to the power x, right? This is an exponential function, of course. A is equal to 2, all right? So so what we are saying is that first there's a y-intercept, which is a 0, 1. So let's say this is here's 1 here. So we do have a y-intercept here at 0, 1. All right. You can make a table of values like let's say here's your x, and here's 2 to the power x. So for example, if x is 1, 2 to the power 1 would be 2. If x is 2, 2 to the power 2 would be 4, etc. Right? So x is 3, 2 to the power 3 would be 8, etc., etc. So then, you can plot these values. So this is, let's say, 2, this is 4, let's say this is 2, 3, and 4, right? Of course, this is 1 here, all right? And so you can, you see, so the 2 to the power 1, we said it's 2, 2 to the power 2 is 4, 2 to the power 3 is 8. So the function is actually increasing. So actually the 2 to the power x would be like sort of this, the graph of the graph of the exponential function 2 to the power x would have this shape, okay? And again, as I said, your graph doesn't intersect the x-axis. So here, you see, guys, here, so there is no intersection. Your graph doesn't cross the x-axis. So you see here, the x-axis would be like sort of a horizontal asymptote for this exponential function. So the x equal to 0, the x-axis. So the x-axis is actually is a horizontal, so y equal to 0. X-axis is a horizontal asymptote for exponential functions. Exponential function 2 to the power x, right? This is the exponential function f of x 2 to the power x. Okay, and actually this is like a general statement. So for any if you have any exponential function, so it doesn't really matter what's a. For any a to the power x, your x-axis is gonna be actually a horizontal asymptote. All right. But anyway, so just keep in mind. So this is exponential functions. Their graph is actually, if you plot a couple of points, you will see that the graph is always increasing. All right. And this x-axis would be a horizontal asymptote. Okay. Because we said there's no x-intercept, right? So you don't cross the x-axis. Anyway, so that's for the general properties of the exponential functions. Let me just introduce some very special exponential function. So when this base a is equal, so there's a special exponential function. So when a is equal to this number e, so there's a number e, very special number e, which is actually approximately, I think it's 2.7182. So the thing is, so the exponential function with base e, okay, then this f of x equal to e to the x. This is a very special function because so you will, you will see in probably in calculus 1, but this function here has a very special property. It's actually equal to its own derivative. So this is very special. It's a special function because, hi Jennifer, is a special function. No worries. Is a special function because, so you see in Calc 1, the f of x would be equal to its derivative. So this is derivative. So the function f would be equal to its own derivative. Okay, so you'll see this in Calc 1. All right. So just keep in mind there is sort of special function, exponential function, when this number a, when this constant a is equal to this special number 2.71, etc. And what's special about this exponential function is that this this function, the function exponential e to the x, would be equal to its own derivative. Okay. Yeah. But anyway, it doesn't really matter for us. It's just for your information. Okay. All right. So we have exponential function. So then I'm gonna define the inverse of the exponential function. So the inverse of exponential function are called logarithmic functions. Okay. So that's the logarithmic functions so this is definition. So logarithmic functions are defined as the inverse They are the inverse of the exponential functions. Okay, so you have your x for positive x. So for x positive, so this is very important. This is a very important hypothesis. Okay, so you have to keep in mind, you need your x to be positive. Okay, so for x positive, the inverse of f of x equal to a to the power x, the exponential function, right, in base a, is, so by definition, it's the function g, which is equal to the log in base a of x. Okay, so this is a log, so log in base a. Okay. So remember, guys, what's the definition of the inverse function? So let me just remind you, what does it mean for g to be the inverse of f? So just to remind you the definition, so g of x is the inverse of f of x if, f composed with g of x is equal to x, and g composed with f of x is equal to x. All right, so that's the definition of the inverse function. Now, if you're going to apply this definition to the exponential and log, so the consequence is the following. So we're going to get the following identities. So the consequence, because of the definition of the log as inverse of the exponential, so consequence of the definition so we would have so first you have this f of g of x is equal to x, right? So then if you apply your f is supposed to be, your f is supposed to be is the exponential in base a, and your g is the log in base a, right? So so f of g of x is equal to x implies that a to the power log in base a. So this is base a. So a to the power log in base a of x is equal to x. Okay, so this is our first identity. Right, so because the f is supposed to be exponential and the g is the log in base a, right? Your g is the log in base a. So when you do f of g of x, that's a to the log in base a of x. And that's equal to x, right? This is equal to x. So that's the definition, right, of the inverse. So it's equal to x. Now, if you do g of f of x is equal to x, so now g of f of x is equal to x. So that implies the following identity. So then you would have log in base a of so the log composed with exponential. So a to the power x is equal to x.
Hello, Professor.
Yes.
Yeah, the zoom makes it we cannot see the whole writing.
Is it better now?
Uh,
I should zoom in or zoom out?
Zoom in.
Zoom in. Okay.
No, zoom out, please.
Zoom out. Okay.
Yeah.
Is it better now?
Yes.
Okay.
No.
You mean like the right side?
Yeah. Now.
Here.
Yeah.
Okay. Sorry about that. Yes. So yeah. Anyway, so that's the that's a consequence of the definition of log. So log, so you have to keep in mind, guys, a log in base a of x, that's by definition the inverse function of the exponential a to the power x. Okay, so when you do f of g of x equal to x, then you get exactly these two identities, right? A to the power log in base a of x is equal to x, and then the second one is log in base a of a to the power x is equal to x, right? So let's do a couple of examples, right? Let's have a couple of examples. So, bless you. So, examples. All right, so first example. Let's say you want to solve for x. Let's say you have log in base 9 of x is equal to 6. So I have to keep in mind, guys, this is so this is log in base 9 of x, right? It's not, this is here. You see here between the log and x, this is not multiplication, right? This is a composition. So you have, when you say log, so you have to apply your log to something. So when you say log of x, so you cannot separate the log from the x, right? That's not, it's not a multiplication. This is, so that's a composition. So that's log of x, okay? So this is, so here, this is log in base 9 of x, right? So you cannot separate the x from the log. It's not the multiplication, right? So it's log of some number, right? So this is log of x in base 9 is equal to x. And I want to solve for x, right? I want to find this x. So how can we solve for x? So what we have to use, guys, we have these two main identities, right? This, the first one is this one here, right? This is first identity, and the second one here, okay? So we have to use these identities to solve for x. So what we have here is log in base 9 of x is equal to 6, right? And I want to solve for x. So what does it mean you want to solve for x? It means that you want to get rid of the log, right? You want to get rid of the log and get the x, right? So how can I get rid of the log? Well, if you use the first identity, you see the first identity, this one here, you have the exponential composed with the log of x, that will be x, right? So in some sense, it's like the exponential and the log, they cancel out, and so you get your x, right? It's like when you compose with exponential, because it's the inverse, right? The log is the inverse of exponential. So in some sense, like this f here and this g, they cancel out, and so you get your x. So the idea, if you have an equation with the log or with the exponential, right? And you want to solve for x. So if you have an equation with the log, you want to solve for x. So the way to get rid of the log is to apply the exponential, because the exponential and the log, they will cancel out, right? So like here, my a here and this log, this is a, this is exponential, and this log here, they would cancel out, and you're gonna get your x. And here the same thing. Here's your log, and this is your exponential base a. So the log and the exponential in base a, they cancel out, and then you can get your x, right? So yeah, I need these two identities, so I'm gonna write them again here. So this is that was what was this? F is okay. So this is, the first one was a. So this was a. Log in base a of x is equal to x. The second one was log in base a of a to the x is equal to x, right? Now, so I was saying, so the idea is here, So you want to solve for x. We want to solve for x. And we have a log. We have a log. Then apply exponential. Okay, because the log and the exponential, they're gonna cancel out, right? So because the log and the exponential, if you compose the log with the exponential, they're gonna cancel out, okay? And exponential, they cancel out. All right. So what do I mean here? Well, so let me write again the equation, right? We have this log. Sorry, I have the trouble with the pen. All right. So log, I have this log in base 9 of x is equal to 6. So I have this log and I want to get rid of the log. So I'm going to apply exponential. So which exponential I'm going to apply? Well, this is a log in base 9, right? So I'm going to use exponential with the same base, which is base 9. So I'm going to write 9 here. Okay. And then I'm going to have this log. So 9 to the power. This is a power. So log in base 9 of x. Right. And the other side, I'm going to also have 9. But the power would be the right-hand side, so that would be 6. So here's 6, right? So you see, guys, I applied the exponential in base 9 to both sides. So here's my 6. That's my right-hand side, and my left-hand side is my log in base 9 of x, right? So what I did is I applied the exponential in base 9 to both sides. So apply exponential base 9 to both sides. Okay, so now because, as I said, if you have a to the power log of a, log in base a, then they cancel out and you get x, right? So this 9 to the power log in base 9, they would cancel out. So this 9 here and this log in base 9, they would cancel out. So you get your x. So here's my x. So my x would be equal to 9 power 6. Okay, so that's my x. So that's the answer. Okay, let's have more examples, all right? So that's just the first example. Example number 2. So let's say I want to solve for x, of course. Solve for x. And so let's say I have, again, log in base 2 of x is equal to, let's say, 3. I want to solve for x, right? So I have this log. I want to get rid of the log and get my x, right? As I said, so what we do, we have a log, we apply exponential. Because exponential composed with the log, it cancel out. So this, which exponential I'm going to apply? Well, this is log in base 2, so I'm going to apply exponential in base 2. So exponential in base 2, so here's my 2, both sides. Now, as a power, in the power, I'm going to put the equation. So on the right side, I have power 3, because that's the right-hand side of my equation. Now, the left-hand side of my equation is this log. So I'm going to put as a power log in base 2 of x. Right. So and then, as I said, so this 2 represents the exponential in base 2, and this log, it represents the log in base 2. So you have exponential composed with a log in the same base, so they cancel out. So then you get your x. All right. So then your x would be equal to 2 power 3, which is of course 8. right? Now, so this is for the log. Now, what about the exponential? So let's say now I want to solve for x. So p. Let's say I want to solve for x. Let's say I have 7 to the power x equal to, let's say, 45. All right. So here, this is on the left side, I don't have a log. On the left side, I have this exponential in base 7, right? This is an exponential in base 7, right? Now, so we're gonna apply the same idea. Exponential with the log, they cancel out. So I have an exponential, so I'm gonna apply a log. So then the exponential and the log, they cancel out, and so I can get my x, right? So this is an exponential in base 7, and I wanna get my log. So I'm gonna apply, I wanna get the x, so I wanna apply a log in the same base. So I'm gonna apply log in the same base to both sides, the same base to both sides. Okay. So then I'm gonna have, here's my log in base 7. Here's my log in base 7. This is 7 to the power x. And here I have 45. Okay. Now, this is the log in base 7, and this is exponential in base 7. So they cancel out, and so I can get my x. So here's my x equal to log in base 7 of 45. All right. Any question, guys? So you see the idea, you have an equation with exponential and some base. So if you want to solve for x, you have to apply log to both sides, of course, in the same base. Now, if you have an equation with the log, so then you have to apply the exponential in the same base to get your x. Okay, so here's an exercise. Okay, so you have to solve for x. Right, so say so first log in base t of x is equal to 4, and then let's say you have 2 to the power x is equal to 1 over 8, right? And then 5 to the power x is equal to let's say 26. Okay. So yeah, so please try to solve for x. All right, guys. So for number one, so we have this log in base 3 of x equals to 4, right? So as I said, you have a log. I want to get rid of the log, so you apply exponential to both sides. So now, which exponential you're going to apply? This is the log in base 3, right? So we're going to apply exponential in base 3. So here's my exponential, base 3. So here's my 3. Is equal. So now for the powers, on the right hand side we have 4. So this is 3 to the power 4. On the left hand side we have this log in base 3 of x. So this is 3 to the power log in base 3 of x. Right? So you put the log and the 4 as the powers. Right? And now because you have 3 exponential in base 3 and this log in base 3, so they cancel out. All right, so then you have this x. So your x is just, so then your x is just 3 to the power 4. All right. Now for number 2, let me know, guys, if you have any question, right? Yes, Crystal. So for number 2, you can say, so you have this 2 to the power x. That's 1/8, right? So this is exponential in base 2, right? This is exponential in base 2, exponential in base 2, right? 2 to the power x. So I'm gonna apply log both sides in the same base. So here's my log in base 2. Here's my log in base 2. This is equal. On the right side, I have 1/8. And on the left side, I have this 2 to the power x. Right? So you have exponential, you apply log. Now, the log and exponential, they cancel out. This log here in base 2 and this exponential in base 2, they cancel out. So it's just x on the left side. So there's this x on the left side. That's equal to the log in base 2 of 1/8. Right? And actually, we'll see later, we can do better than this. So next, I'm going to show you a couple of properties of the log. So then you can do better than this log in base 2 of 1/8. But let's say for the moment, that's the answer. Okay, that's our answer. For number 3, the same idea. So it's 5 to the power x equal to 26. So for number 3, so it's 5 to the power x equal to 26. So on the left side, I have an exponential. This is exponential in base 5, exponential in base 5. So I'm going to apply log both sides. So here's log in base 5, log in base 5. On the right side, I have 26. So here's my 26. And on the left side, I have this 5 to the power x. All right, so then log and exponential cancel out. So this log and exponential, they cancel out. So it's just x on the left side. And on the right side, that will be log in base 5 of 26. All right. Any question, guys? All right. So then, okay, next, I'm going to show you. So there are some, so log has very special properties and very useful properties. So properties of the log. So properties of f of x equal to log in base base a, sorry, in base a of x. Okay. So first, I have to remind you guys, so when you have f of x equal to log, in base a of x, your x, then x must be positive, okay? X must be positive. If it's not, so log in base a is only defined for positive numbers, okay? So then x must be positive. Okay, it's like saying square root of negative numbers is not is undefined, right? Square root of negative numbers are actually complex numbers. So the same here for log. You need your x to be positive. Otherwise, so log of negative numbers or log of 0, it's actually undefined. Okay, so log in base a of 0 or log in base a of negative numbers is actually undefined. So log of 0 and log of negative numbers are undefined. Okay, so this is, so we have to keep in mind that log is only defined for positive numbers. Number 2, log of 1 in any base. So this is a second property. So f of 1, so log in base a of 1, so log of 1 in any base is actually equal to 0. This is equal to 0, okay? Always equal to 0. All right? The reason is because if you do, you have log. So let's say you have log in base log in base a of 1 is equal to some number. Let's say a number x. All right. So we want to get rid of the log. You apply exponential in base a. So here's my exponential base a. Here's my exponential base a. So then you're going to have a log a to the power log in base a of 1 equals to a to the power x. As we said, this a and this log, they cancel out. So actually you end up with 1. This is 1 here. 1 is equal to a to the power x. So for which number x, a to the power x is equal to 1? Well, that's when x is 0, right? A to the power 0 is equal to 1. So a to the power 0 is equal to 1, right? So then x is equal to 0. So this x here, this one here is equal to 0. Okay, so that's why log, log in base a of 1 is always equal to 0. It doesn't really matter what's the base a, right? So log of 1, keep in mind, log of 1 is always 0. Okay, that's another property of the log. F of 1 is always 0. Next property is when you have a product. So we have, if you have log in base, let's say base a, log in base a of x times y. Okay, so then because the log is the inverse of exponential, right? So because of that, then we can deduce that the log of x times y is actually equal to log in base a of x plus log in base a of y. Okay, so for example, let's say you have log in base a of, or log in base, let's say 2, in base 2 of 15.
Professor,
Yes. Yeah.
I'm sorry, I have a question. I
Yeah.
couldn't do it. My computer was kind of frozen, but
Yes.
I had a question about the first exercise. I got an answer of x equals 81. Would that be okay also, or it has to be expressed as an exponent? Like it has to be 3 to
The
4.
3 to the power 4.
Uh-huh.
Yeah, both are correct. I mean, of course, 3 power 4 would be 81. Sure.
Oh,
Yes.
okay.
Yeah, I just
Okay.
yeah. I just
Just
keep
making sure.
yeah.
Okay.
Yeah,
So
both are
either
correct.
answer will be okay.
Yeah, either answer are okay.
Okay, thank you.
Sure. Yeah, so this log in base a of x times y, that's a log. So log of a product is the sum of the logs. Okay, so for example, log in base 2 of let's say 15, that will be equal to log in base 2 of, let's say, because 15 is 3 times 5, right? So then that will be log in base 2 of 3 plus log in base 2 of 5. Okay, that's because 15 is equal to 3 times 5. Right? So if you have a log of some number of a product, then that will be the sum of the logs. Okay. Now, so that's for the product. Now, if you have a division, a log of x over y, this is 4. So if you have log of x over y, base a, so log in base a of x over y. So if you have a division, then actually it's going to be, that will be equal to the difference between the logs. So it's going to be log of in base a of x minus log in base a of y. Okay, so for example, okay, so say you have this log in base 2 of 1 over 8. Okay, so that's 1 over 8. So then we said a log of, if you have a division, then that will be the difference between the logs, right? So that will be the difference between the log in base 2 of 1 minus a log in base 2 of 8, right? Because it's 1 over 8. So then that will be the difference between the logs, right? But then, guys, remember, we said a log of 1 is always 0. It doesn't really matter the base. We said log, you see here, log of 1 is always 0. Okay, it doesn't matter the base, right? So log of 1 here, this log here, that's log of 1, that will be 0. So this is actually equal to 0 minus log in base 2 of 8, right? So that's minus log in base 2 of 8. All right. So that's another property of the logs, right? Log of division, that's the difference between the logs, okay? Now, another important property of the log, so we have a log of product, that's the sum of the logs. Log of division, that will be the difference between the logs. Now, if you have a log, last important property is the following. If you have log, say log in base a of, let's say, x to the power b, all right, then actually what you can do is you can bring down this power b to the front. Okay, so then that will be b times the log in base a of x. Okay, so if you have log of x to some power, then you can actually bring down the power in front of the log. So that will be the b times the log of x. Okay, so for example, so here I had, here I had this log in base 2 of 8, right? So then I can write it like, so this log in base 2 of 8, 8 is 2 to the power 3, right? So that's a log in base 2 of 2 to the power 3, right? Because 8 is equal to 2 cubed, right? 8 is 2 cubed. So then, because 8 is 2 cubed, then I can actually, this power 3, I can put this, bring down this power 3 in front of the log. So that will be actually 3 times log in base 2 of 2. Okay. So if you have a log of some number to the power, some power, then you can always bring down the power in front of the log. Okay. And then what else? Yeah, last property is the, so we said log of 1 is 0, but then if you have a log, so property number 6, so 6, if you have a log in base A of A, so log in base A of A, that's always equal to 1. Okay, so if you have a log of some number in the same base, that's actually equal to 1. Right, so for example, so if you have a log in base 2 of 2, log in base 2 of 2, that will be equal to 1. Okay, or log log in base E. Remember, we talked about this special number E, which is the 2.71, etc. So log in base E of E, that's also equal to 1. Okay, so whenever I have a log of some number in the same base, then that will be just equal to 1. Okay, and that's because you can solve. You have this log in base A of A. You apply exponential to both sides, so you're gonna have your the solution would be 1. So for example, we have this log of in base 2 of 8. So example number 3. Example number 3. So we had this log in base 2 of 8. So we said, remember, we said that we can write 8 as 2 cubed. So that's log in base 2 of 2 cubed. And then we said when you have a log of some number to some power, then you can, you can bring down this power in front of the log. So that'll be, 3 times log in base 2 of 2. But then this log in base 2 of 2, this one here, this log in base 2 of 2, that will be equal to 1, right? That's what was just we said, right? The log in base A of A is 1. So that's equal to 3 times 1. So this is 3 times 1, so that will be equal to 3. All right. So yeah, so we can use all these properties, to solve, if you have like a log or exponential equation, you can try to use all these properties to solve your equation. So so here's an exercise, guys. Exercise. So try to simplify the following logs. So simplify when it's possible. Okay, so number 1. So let's say you have log in base 3 of, let's say, 27. Number 2, log in base, let's say, 2 of 1 over 16. Okay. And then number 3, last one. So log in base, let's say, 3 of 1 over, let's say, 1 over 81. All right. So let's say you have 5 minutes, guys, to think about this exercise. So any guess for number one, guys? For number one, Crystal, probably you mean 3. Yes. Yeah, 3 would be correct. Yes. Absolutely. And what about number 2? Yes, Carolina, correct. Very good. -4. Very good. And last one. Yeah, -4 as well. Yes, very good. Very good, guys. Yes, so so for number one, guys, this is so it's log in base 3 of 27. So the idea is to write your 27 as a power of 3. So I mean 27, it's 3 power 3. So so it's log in base 3 of 3 to the power 3. And then because 27 is 3 cubed, right? So then you can bring down this power in front of your log right here. Okay, and so that'll be 3 times log in base 3 of 3. All right, but then we said log in base a of a, it's always equal to 1, right? So just to remind you, so log in base a of a, this is always equal to 1, okay, for any positive number a. So then log in base 3 of 3, that will be 1. So this thing here, this is equal to 1. Okay, so this is so that's 3 times 1, which is equal to 3. All right, so you see how it works, guys? You write your number as a power, some power, and then use the fact that this, this log in base a of a is 1. So then, and then so you can simplify your answer. So, any question, guys, about number 1? All right, so for number 2, so first we have 1 over 16. 1 over 16, it's so that's a division. So this is number 2. So it's log in base 2 of 1 over 16. So when we said when you have a division, a log of a division would be the difference between the logs, right? So this is the difference between the log of 1, so minus the log in the same base, of course, which is 2, of the denominator, which is 16. Right? So log of the division, that will be the difference between the logs. Now, log of 1, we said the log of 1 is always 0. All right? So remember we said, guys, log of 1 in any base, log of 1 is always 0. So this log of 1 right here, this log of 1, this is 0. Okay, it doesn't matter the base, a log of 1 is 0. So we're going to have now 0 minus log in base 2 of 16. So that's negative So that's negative log in base 2 of 16. Now, what we can do is we can write the 16 as a power of 2. 16 is 2 to the 4th, right? So this 2, this is equal to negative log in base 2 of 2/4, right? Because 2 power 4, that's 16. Now, you can bring down this power in front of the log right here. So that would be, there's a minus, of course. Don't forget there's a minus. So here's my minus. And then there's my 4 times this log in base 2 of 2. But then we said log of A in base A is 1, right? Remember here, guys, that's the rule. So this log in base 2 of 2, that's equal to 1. Okay, so that's negative 4 times 1, that will be equal to 4, negative 4. Right, and that's the answer. So you see, guys, you can combine all these useful properties of the log, so then you can simplify your answer. Okay. Number 3, we had log in base 3 of 1 over 81. So number 3. Log in base 3 of 1 over 81. So this is 1 over 81. Again, it's a division. So then the log would be the difference between the logs. So here's my log of 1 minus the log of 81. This base is 3. So here's my base 3. Right? And then we said log of 1, it doesn't matter what the base, it's always 0. So this log of 1, this is 0. Okay? Log of 1 in any base A is always 0. All right, so that will be 0 minus log 3, log in base 3 of 81. Now I can write this 81 as a power of 3. That will be 3/4. So this is again, so it's going to be 0. So it's minus log in base 3 of 3 to the 4th power 4. Right? 81 is 3 to the power 4. Then I can bring down this power 4 in front of the log. So that would be negative. There's a negative. This is my 4. Log in base 3 of 3. And then we said log of A in base A is equal to 1. So this is this log, as like for the log in base 2 of 2 is 1. So then the same log in base 3 of 3, that's equal to 1. So that's negative 4 times 1. And so the answer is, again, negative 4. All right. Any question, guys? So yeah, so we have all these important properties of the log. So we have to, you have to remember all these properties because they are kind of very useful, right? So you see here they are very useful when you want to simplify your log, right? Any question, guys? All right, so then we can move to solving log and exponential equations. So let me just mention one thing here. I forgot to say, when you have a log in base E, remember we talked about this special number E. So when the base, so when A is equal to this number E, special number E, joint, this 2.7, oh, what's going on here? So this is 2.7, oops. Okay, so for some reason I lost the board. Okay, anyway, I was about to move to the next page. So my remark was the following, guys. So I was saying when your base A is equal to this special number 2.71, 85, I think. All right. Then the log in base E, actually it's called the natural log. So it's denoted by ln. So ln means natural log. That's the log in base. This is a natural log. So when I say natural log or ln, that's the log in base E, right? Okay. So all I'm saying is that log in base E, this is a special number E, has a name. It's called natural log, ln. Okay. So if you see ln, that means natural log. That's the log in base E. That's just a different name for log in base E. All right. Anyway, yeah, I said now we can solve logarithmic exponential functions. So let's move to the equations now. I'm gonna solve logarithmic and exponential equations. And exponential equations. Right. So I'm going to start with an example. Examples. I'm going to do probably 1 or 2 examples. We're going to start with the logarithmic equations. So let's start with the first example of the logarithmic equation. So let's say you have log in base 2 of x plus 1 minus. So here, when I say log in base 2 of x plus 1, so again, you cannot separate the x plus 1. It's log applied to the x plus 1, right? So first, you need to do the x plus 1, what's inside between the parentheses, the x plus 1, and then you apply the log, okay? So it's log of x plus 1, okay? Minus log in base 2, let's say it's x minus 2 equals to 1. Okay, and of course, I want to solve for x. I want to find the values of x which satisfy this equation, right? I want to solve for x. Let's say this is a plus. Let's start with the plus, and then we're going to do the minus. So as I said, so this is the log of x plus 1. So you cannot separate the log from the x plus 1. All right, and then there's a plus log in base 2 of x minus 2 equals to 1, right? So the problem is, so I want to get rid of the log, right? But the thing is, I have 2 logs, right? I have this log of x plus 1, and there's this log of x minus 2. So the idea, the first step, if you have more than 1 log, then the first step would be to combine all the logs in just 1 log. Okay, so first step, so step 1. So step 1 is to combine all the logs in just 1 log. Okay. So I have 2 different logs here. I have this log of x plus 1, and I have this log of x minus 2, right? So how can I combine these 2 logs in just 1 log? Well, remember, guys, so let me just remind you, we said one of the properties of the log. So if you have log in base a of x plus, so if you have a sum of 2 logs in base a of y, so then that will be the log of x times y, right? So remember, we had this example of log of 15. We said log of 15, for example, would be log of 5 plus log of 3, right? Because 15 is 5 times 3. So if you have the sum of two logs in the same base, of course you need the same base. But if you have the same sum of two logs in the same base, so that will be the log of the product, right? That's one of the properties of the log. So here, my base, I have the same base. This is here's base 2. Here's my base 2, right? I have the same base. Now, this x here would be this x plus 1. This y here, that will be this x minus 2. Okay, so this is the sum of these two logs. That will be the log of the product. So we're going to have log in base 2 of, so I'm going to have x plus 1 times x minus 2 equals to 1, right? That's because of my property. If you have a sum, if I have the sum of two logs, then that will be the log of the product. Is this step clear? Any question about this step? So I'm using one of the properties of the log, right? Remember, we said log of product, that would be the sum of the logs. So if I have here a sum of these two logs, so that will be the log of the product, right? Now, that's the first step, right? I had two logs, so I combined the two logs in just one log. Now, next step, again, I want to solve for x. That's the goal, right? I want to solve for x. Now, because I have one log, only one log, I can get rid of the log, right? Using the exponential. So step 2 would be to get rid of the log using exponential. So step number 2. That's step number 2. Apply exponential, same base, to get rid of the log. Okay, so what's my base here? My base is 2. This is log and base 2, right? This is base 2. So I'm gonna have base 2, exponential base 2. I have my equal on the right hand side. I have 1. So here's 2 to the power 1. So you have the power would be 1 on the right side. On the left side, the power would be the whole right side, left side. So that's a log in base 2 of x plus 1, x minus 2. Right? So then my log and my exponential, same base, they would cancel out. So this 2 and this log in base 2, they would cancel out. So now I'm going to have just x plus 1 times x minus 2 equals to 2. So you see, guys, I started first, I had an equation with two logs. I combined the two logs in just one log, and then applied the exponential to get rid of the log. Right. So now I have just have an equation with just x. So I can solve for x. You can expand the let's say the left hand side. So this is x times x. That will be x squared. You just distribute here. This is x times x, x times 2. So that's minus 2x, and then there's plus 1, plus 1x, and then plus 1 times a negative 2. So it's plus 1x, and this negative 2 is equal to 2. All right, so this is actually just a quadratic equation, right? So I'm going to subtract 2 both sides. So that's x squared minus 2x plus x minus 4 is equal to 0. There's this minus 2x plus x. That will be x squared just minus x minus 4 is equal to 0. Right? So this is now just a quadratic equation, so I can solve for x. So then my x would be, minus b, so minus negative 1 plus or minus square root of b squared, that's 1, minus 4 times a times c, which is negative 4, over 2a, 2 times 1. Right, so then your x is positive 1 plus or minus square root of, so minus minus, that would be a plus, this minus here, minus plus, 16 plus 1 is 17, so that's plus or minus square root of 17. So 17, square root of 17 is not an exact square. So I'm gonna just keep the square root of 17, sorry, over 2. So we're gonna have two solutions. So then x, it's 1 plus square root of 17 over 2, or x is 1 minus square root of 17 over 2. Okay. Now, we are not done yet. Okay, so there's the last step. So those are possible solutions. There's one more step, guys. We have to check that your solution is well defined, because remember we said we can only apply log for positive numbers, right? So for example, in our case, I have this x plus 1. This x plus 1. So x plus 1 must be positive, right? Because we said we can only apply log on positive numbers. So this x plus 1 must be positive. This must be positive. Must be positive. And your x minus 2 also must be positive. Must be positive. Okay, so this is your initial equation, right? So we have to make sure that your x plus 1 and your x minus 2 are positive. So now I got so two solutions, possible solutions. So I have to check if my x plus 1 and x minus 2 are positive. So this is the last step, step 3. So step 3, so we have to check if your x plus 1 and x minus 2 are positive. Okay. So if x is 1 plus square root of 17 over 2, so this 1 plus square root of 17 over 2, this is, square root of 17 is approximately 4 point something, and then plus 1, that will be 5 point something, over 2, that will be 2.5 or 2.6. So this is approximately, if you use a calculator for a square root of 17, so this is this is approximately 2.5, right? This is approximately 2.5, right? Or 2.56. Thank you, Carolina. So then the question is x plus 1 and x minus 2, are they positive? Well, yes. So x plus 1, so the 2.5, so the 2.56, so then 2.56 plus 1 and 2.56 minus 2, both are positive. Okay. Okay, so then x equal to 1 plus square root of 17 over 2 is the solution. Okay, so then that's a solution. That's a real solution, right? Now, what about the minus 1 minus square root of 17? Now, if x is 1 minus square root of 17 over 2, so that will be approximately, so it's gonna be like negative 3, negative 3 point something over 2. That's negative 1 point. So it's gonna be like negative 1.5 something. Okay. Now, if you do plus 1, right? I have two conditions. I have x plus 1 and x minus 2. They must be positive, right? That's the definition of the log. Log is only applied on positive numbers. So if I have log of x plus 1, I have to make sure that x plus 1 is positive. So then this negative 1.5 plus 1 is negative. Okay. Okay, so if it's negative, if one of the if x plus 1 or x minus 2 is negative, then it's this solution must be rejected. So we have to reject the, so that's negative. Okay, so then x equal to 1 minus square root of 17 over 2 is rejected. So we have to reject this solution because my x plus 1 is going to be negative, not positive, and that's not possible. That's undefined, right? So then final answer, I got only one real solution, which is the 1 plus square root of 17 over 2. Okay. So then final answer. So final answer. So the solution is x equal to 1 plus square root of 17 over 2. Okay, so we have only one solution. Okay. Here I meant, of course, are positive, right? This is, they're positive, right? The 2.56 plus 1 and 2.56 minus 2 are positive, so they're okay. All right, so that's why this 1 plus square root of 17 over 2 is actually is a solution. All right, guys, I guess I'm gonna stop here. So next time, so we're gonna meet next Monday. We're gonna finish, I'm gonna continue with this log and exponential equations, and then I'm gonna start the trig functions. Okay, so we're gonna continue with this next time. So we're gonna meet next time. That will be next Monday. Okay, so no lecture on Wednesday, and we're gonna meet next Monday. All right. Thank you, everyone. Thank you, guys. I will see you on Monday. Happy Thanksgiving. All right.
Professor,
Yes.
we don't have class on Friday.
No. Well, this is Thanksgiving, so there are holidays. Thursday and Friday are holidays.
Okay.
Sure.
Thank you.
Have a good day. See you next time, guys. Take care.